Guten Tag.
Hello, my name is Tobias Breik, and today I will use the fringe pattern projection system to provide some insights into optical metrology. What is fringe pattern projection? Fringe pattern projection is a method to capture part surfaces in 3D. It works by using a sensor. I will present it to you today with our ATOS compact scanner. We've set up two cameras, left and right, and in the middle we've got a projector. The projector projects a fringe pattern onto the part which is captured by the left and right camera. This fringe pattern encodes the part's surface. Every camera has a pixel matrix. Every pixel represents a measuring point on the part's surface. This encoded surface of the fringe pattern allows each camera to detect one measuring point. They thus have a length and a calibrated distance between the camera angles and are now able to compute the point on the part's surface. Let me give you a live demonstration with this injection molded part. I'll start a rotary table measurement. As you can see, the sensor captures images from different perspectives of the part to ensure full field digitization. You can watch the part as it slowly builds up in the software. Okay, we scanned the top. The bottom is still to go. The sensor cannot look through parts. This is why I take the part, turn it around, and reposition it on the rotation table, and initiate the next scan. Again, the sensor requires several images, several perspectives. Okay, we captured front and reverse, but the positions do not match yet. I'll align the two halves to each other by using the reference points on the part's edges. By simply selecting these reference points, and now the software aligns the top and bottom to each other. So, and now we can see that they have the same orientation. The next step would be to polygonize the data into an STL to end up with a planar object to continue with the process. I've already prepared everything. Here we have a completed STL. Next, I need the elements CAD data, which I import into the software via drag and drop. Logically, the two are again separate from each other. So let's do a pre-alignment first. Okay, and now we've aligned the actual part to the CAD part. Right here you can see the gray areas representing our actual part and the blue areas representing our CAD part. Already here you can see where the actual part is superimposed on the CAD, where we have deviations. Of course, you can also visualize it as a false color comparison. The colors help you to discern quite easily where does the part have sink marks, where is it warped. Blue areas mean I don't have enough material, so there is a minus. Yellow areas mean I've got excess material. That's where my part bends upwards. I can also adjust the color scale and even fine-tune it. Plus minus 2/10. The deviations are now more prominent. You can see that this area is clearly bent upwards and the areas to the left and right slope downwards. Okay. The colors and color scale describe more or less in which area I am. Of course, I can also create deviation labels to identify deviations in specific areas. Next, I'll define an inspection section to display this area, the profile of this middle part. First, I define the plane, the direction and position in which I want to create the section. Then I select the area where I want to have the section. And create the section. Here you can see the color deviation. Again, you can adjust the color scale. And you can also create deviation labels. This time I'll use the feature equidistant deviation labels. I'll input the distance right here. And here are the deviation labels on the section, evenly distributed. We're now in a pre-alignment, that is a best fit, the best possible alignment of the cut to the part. Of course, you can also define all subsequent alignments. In this case, I'll construe surface points to define an RPS alignment. I'll take 3 points on the Z plane, fix 2 points for the Y orientation, and 1 last point for the X orientation. Finished with the points. I'll switch to the alignment and import the points I want to use for my alignment, and now I can select the individual axes where the points will take effect. The first 3 of them define my Z plane. Points 3 and 4 define my Y direction, and the last point, the X direction. I confirm everything, and now I've aligned my part using these 6 points. Now let's take a look at this by returning to the false color comparison. We are now in the RPS alignment. You can see that up here I've aligned the part according to the green areas. Accordingly, you have more blue areas down here. Now when we return to the pre-alignment, the best fit, and we watch the colors changing during the surface comparison, and the part returns to a slight mismatch. Here we rebalanced everything, blue areas up here and blue areas down here as well. Right. Of course, we can use not only surface points for alignments, we can also use all kinds of elements, such as circles, surfaces, planes, whatever the drawing specifies. Since we're talking about the drawing, naturally, we can also define boreholes. Let me demonstrate this with 4 circles. I'll define the circles for the cat. Here are the circles for our cat. I'll have to tell the software how to compute those circles for the actual element. And that's where our measuring principle comes in. For the circles, I will define at first, as with tactile measuring machines, a plane where I define the circle's orientation and then the depth at which I want to measure the circle. And now I've created the circles. Now I can visualize the diameter and also the XY position. You can see those labels for the circles with the x-coordinate, the y-coordinate, and the diameter. I've got the nominal value, the actual value, and the deviation, and now I can assign a tolerance to each value. And I can see each result in a different color. Green means within tolerance, red and blue means outside tolerance. Here you can see a red bar outside tolerance, a green bar within tolerance. Next, I want to measure distances from those circles. I'll select a distance, the 2-point distance, then select my circles in the software, and now I can define whether I want to compute the direct distance between the bores or the paraxial distance. In this case, I'll select the paraxial distance in y direction. Pull it outward as specified in the drawing. And compute a second distance in x direction. Again, I'll compute the paraxial distance for the x direction. And also, I can assign my tolerances right here. And again, I'll pull this one out as well to ensure that you still have a good overview. Okay, I could go on with all kinds of elements. I can compute the position, I can compute angles, different distances of planes, lengths, widths, etc. Of course, I can sum up everything in a report. Let me demonstrate this. The report normally starts with a cover sheet. I've got the table of contents, an image of my surface comparison. For instance, an inspection section, an image and tables with geometric dimensioning and tolerancing. Flatness right here, even with a false color representation, so I can see where flatness has defects or where I might have to correct flatness. I've got different distances, as we've just computed, or I can also assign the point designations in an image or list them in a table based on a p-pad measuring report. The entire system I've shown to you is a semi-automated system. I've positioned the sensor on a tripod and the part on an automated rotary table. We've got another automation where I can mount the sensor on a rotary swivel table, which means I've got a rotary table whose position I can also swivel. The sensor, whose height I can automatically adjust, but also the fully automated solution in a scan box, where the sensor is attached to a robot. And the part is on a rotary table, so that I can perform fully automated measurements during ongoing production. So much for knowledge track 1. I hope I was able to provide some information on optical metrology.